Hello everyone. In this video, I'm going to explain auxiliary equations with complex roots. We're still in the subject of linear second order equations, and this is the other case in which a discriminant comes up to be negative. This video is about the background behind the kind of the formula you use to solve. So I'll do another video with directly going into the examples. But if you want to understand where that came from, which helps with memorizing and maybe deriving as well, then this is kind of the video for it. So the first thing to talk about is the simple harmonic motion, which you've seen in trigonometry and if you took physics and other courses. Also in here, the simple harmonic equation. Remember, the middle term is gone because there is no damping. You get something like this. And it's called harmonic because it's connection to musical tone. And if you connect this with previous knowledge, like you've seen the type of solutions to be something like this. So, however, if we look at the auxiliary equation or the characteristic equation, it's r squared plus 1 equals 0, which gives you r equal plus or minus square root of negative 1, which is plus or minus I. And of course, some engineer courses, they may use J for I. Doesn't matter. And in the previous sections of linear second order equations with constant coefficients, of course, we expressed this in terms of exponential function. So previously, let's do this. Previously, we kind of expressed solutions in terms of, remember R, let's say 1 T R, R2T, right? So it would kind of appear that we need to connect these. We need to connect somehow these exponential forms with the expected parts that show up for this type of problem, right? So that's kind of the question, and this matchup is accomplished by Euler formula, is done by Euler's formula, which is a really interesting formula. I'll show you how it was derived in kind of, it looks, after you see it, you're like really kind of nice and easy, but it's really one of the amazing formulas in math. So let's discuss this. If you have a differential equation, let's say that the type we're looking at is linear second order, which gives you its characteristic equation to be this. And now, if b squared minus 4ac, the discriminant is less than 0, then what happens? Here, I'm going to explain a really nice thing, a trick in math. If you haven't done it, here it is. Let's talk on the side. If I have negative, a square root of negative 3. It's I square root of 3. But really what happens is you have I, the opposite of what's there, right? And that brings the idea of if I have 2 minus 5, which leads to a negative number, how can I rewrite it and introduce the opposite? I just need to do then this, because 5 minus 2 is negative, and it's, 5 minus 2 is positive and negative here. Now it's negative, right? So if I have b squared minus 4ac begin, let's do, maybe give it an example like 2 minus 5, then I can rewrite it as 4ac minus b squared, right? That's right. So when it is under a square root, the negative we know is just square root of -1, and 4ac minus b squared is going to be I square root of 4ac minus b squared. So if b squared minus 4ac is negative, then 4ac minus b squared is positive. Okay, so this, I will use this in setting up the quadratic formula, because our interest is b squared minus 4ac is negative. All right, so now let's write. Let's do these here. All right, if b squared minus 4ac is negative, then we run into two complex solutions, but quadratic formula is usually written this way. Then now we want to say, maybe, like college algebra, we say, then we have two complex solutions, then after you put the numbers, then I show up. But here we'll make it show without using the numbers, because I'm going to use now this part here. All right, so R1 and R2 are negative b over 2a, which is this, and we still have a common denominator, so plus minus this screen here. All right, so I will change this to this. Now I'm going to use this idea, I square root of 4ac minus b squared over 2a. You see, that's really pretty cool, knowing that b squared is minus 4ac. We can rewrite the equation without even putting any numbers and show I. Okay, so now what we will do is we will say, well, this is some alpha and this is some beta. Okay, so alpha is going to be always this, and beta is going to be always this. So we're going to introduce these, which give us to write R1 as alpha plus I beta here, and R2 is alpha minus I beta. Okay. And of course, I square root of -1, and we put what alpha is and what beta is. And we're ready to keep going. But before we do that, let's show you something that we may run into. We may run into this type. So, and remember, we're thinking that maybe we should connect these exponentials with this cosine and sine. So what if the r, is, so now look at the e. What if it's, let's say, r1 t? What else I can do with it? So, all right, let's look at, let's say I put r1t, right? r1t. So e alpha plus I beta t. Here now you can distribute. And with the exponents, you can change this to multiplication. So that's kind of the interest. And now to work with this, you're going to see how Euler came up with this thing. Now got to this point, I'm like, okay, we're trying to connect these with these. And if the complex case happen, the best we can do is rewrite them as these. So if somehow, we put them on these exponential, this is the best we can do. So how can we switch to these cosine and sine that these problems are known for? Well, this is where Maclaurin series are going to come. And I'll give you a review a little bit about it and talk about it because they're powerful. And unfortunately, sometimes in maybe like calculus 2, they're done towards the end. And if they're done towards the end, then maybe there isn't a lot of practice on it. Okay, so just to tell you a little bit about the Maclaurin series, they are a powerful math tool, and they're useful in approximating functions near the origin. That's why you'll see that they are like special case of Taylor series because we're using x naught as 0. They're good at analyzing function behavior, of course, near the origin, and solving problems in different fields for scientists and engineers. And they are efficient. They are powerful in a way that they offer efficient calculation because the representation of them, like power series or infinite sum, or acting like a polynomial, helps in having an efficient computation. Okay, so if you remember its formula, the compact one here on the left is the sum as n equals 0 to infinity, the nth derivative at 0 x n over n factorial, then you can expand it. So now, what is this for I theta? Of course, you're gonna have the first one here, EI 0 will be 1. Then the first derivative is going to give you EI theta, and x here theta. So it's going to be I theta exponential power I theta. All right, then you keep going. Now you do the second derivative. That's going to be the I square and theta square. So we just do both squared. And let's see here. Let's stop here. Yeah, let's, I think just do it because for 0, because we're doing Maclaurin series for it. So if it's 0, this is going to be 1. And it's going to be 1 throughout. Okay, so I think just to simplify. Then over 2 factorial. Excuse me. Then you just keep going until we get to the kth derivative, or and towards the end, whichever you want, but you can't see the pattern. If it's if you get to some k, you're just gonna have this, right? But here, as you see, you have terms that have I, and terms that don't have I. Like, for example, 1 that doesn't have I, then you'll say, oh, this has I, but this is I squared, it's -1. So I to the 4th is going to be 1, right? But I cubed is going to be -I. Kind of like go through that when you go through it, um, and you simplify them, you will get that some terms, maybe rewrite it, you get this, but you see now the second one, simplify the I squared, we get this. Then I cubed is going to be -I, so it's going to be and I to the 4th is going to be 1. So we get this. Okay. And from here, you can see that you have terms that have I and terms that don't. So if we collect them, I think let's just write it here. You see the ones that don't have the ones that have the even powers don't have any I, of course, remaining, and the one that have odd powers have I remaining. And if you factor that I for all these terms, you're running into this kind of formula here. All right. So now what's going on here? If you recall, Maclaurin series, it's in the right. Let's see. For cosine theta, it's 1 minus theta squared over 2 factorial plus theta to the 4th plus 4 factorial. So it's really this. Then if you recall, sine of theta is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus this, which is really this. So what we have here is Euler formula, which is cosine theta plus I sine theta. And of course, let's write it here. And what can we do with this Euler formula? we'll go back to, remember, if you run into this type of solution that has this part, and we can rewrite it as this. So now we can use Euler formula to rewrite I beta t. So if I have some like this exponential with alpha plus I beta times t, which is E alpha t times e to I beta t. So E alpha t remains. Now we can rewrite using this. You see, I theta, 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 and I. Okay, so we'll just redo the formula here for it. So it's going to be cosine beta t plus sine beta t and I here, which kind of expresses the complex function in terms of familiar real functions. And having made this sense, we can now, of course, show that we can even do that if you need to do a derivative. Now we can show that if you do derivative with respect to time, it's going to be this, right? And with the choices of alpha and beta, as of course given in this equation, remember alpha and beta here. Let's see if it wants to pick up. Yeah, yeah, they are, right? Then the complex function that this complex function here is indeed a solution to the equation. And we can write, of course, the solution y of t as the arbitrary constant c1 times exponential with the power here as alpha plus I beta t plus c2 alpha plus minus I beta t. All right, so now let's replace there it is. So you see, it looks long, but now understanding where it came from, it's not a big deal. All right, so we can do a little more to it. We can do examples, but I'll do a video with examples. And as you will see, of course, if you have an initial value problem, you will do y prime, and this is a little bit long. So we may need to think about or seek an alternative pair of solutions to this differential equation and don't require kind of complex arithmetic And we can introduce a lemma here for that transition. Which says that if you have some complex here, be a solution of course this differential equation when A, B, and C are real numbers. These are real numbers. Then the real part, and the imaginary part are real valued solutions. We call them real valued solutions. And you will see why, because of course we run into this complex arithmetic, then we want to find some alternative pair of solutions for these, and these lemmas suggest that if you have this, and these actually UT and VT are real solutions, and there is a nice proof to it. It doesn't take too long to do, which if you're interested in doing, you will replace for, let's say, of course, y double prime, y prime, and y, you will replace with this u, with this z here, you will replace with u and iv. So you will replace, let's just give you a quick idea of the proof. So if we have this, and of course, z is u plus iv here, are we gonna get something like that will show that u is a solution and v is a solution? Yes. So I recommend you try it. Of course, you take a second derivative, you take the first derivative, you replace them here. Then this is just z as it is. Then you will collect the real parts and you get something like this, of course. Then, but a complex number is zero, right? So this will run into a complex number to be zero, only if and only if this is zero, and of course this is zero. So a complex number cannot be zero unless these two parts are zero, which prove that you see u substituted there just like a y. So when we say y is a solution, so u is a solution and v is a solution. You see, so it's a quick, nice proof that actually shows that. And now I'll give you the summary and conclude this video with this. So what are the complex conjugate roots? If the auxiliary equation has complex conjugate roots. All right, so if we have alpha plus, remember we wrote them this way, are are complex conjugate roots. Of course, for the this. Then two linearly independent solutions are then two linearly independent solutions are E exponential alpha t cosine beta t and E exponential alpha t sine beta t, and a general solution is y of t equals C1 E exponential alpha t cosine beta t plus C2 E exponential alpha t sine beta t, where C1, of course, and C2, as we've done, are arbitrary constants. And now you know the formula that you need in this case. So it's actually kind of, when we get to solve this type, it's actually easier. You see how in a long way we got to it. So we kind of looked into some important details concerning complex numbers, complex valued functions, and of course, further analysis is going to be required to justify kind of law of exponents and a little more work. But I think I'll conclude the video here, and we'll do some examples, and if we have to go and talk about some other cases like over damping and stuff, we will do. Thank you.